Welcome to Dr. Data Science Office Hours. This session are every third Wednesdays of every month at 9 a.m. Pacific. The session recordings will be posted on YouTube. And today we have Stephen Hillen and Nico Road with us, who would be presenting today's session.
Hi, Nima. How are you doing?
Hi, hi, Stephen. You can continue from here so that you can give an information on what was our last session, and then we can continue towards our topic.
Super. Great. Thank you so much. So yeah, last time we looked at ways of using predictive models to not to actually predict, but of ways of exploring data, and also popular charts used in exploration of data. You can find that on YouTube. This week, we're going to start out by looking at big data. That's a topic that's frequently talked about, rarely actually defined. And we're also going to talk about neural networks, which is a topic that's frequently talked about, but rarely actually used. So let's get going. Nico, I know you and I have both worked in the area of big data for a while now. What actually is a good definition of big data? What is it?
Yeah, that's a good question. I think you're right. It's something that I think gets thrown out a lot, or thrown around a lot, and something that you never really get into the weeds with, right? A lot of people say big data, but what does that actually mean? Well, I think it's important to take a look at big data as a trend, right? It's been around for a long time, at least in the terms of the tech world, right? There's been a huge increase in trend and interest as to what big data is. And then also correlated to that is an increase in the trend of what is the Internet of Things. And I'm going to explain this in a second, but to answer your question sort of right off, I think big data is data that is too big, in terms of size, to be held on your desktop computer, right? The sort of paradigm you're used to, maybe of having your local desktop and writing a script to sort of sift through data or analyze it. When we're talking about big data, it's big data that doesn't really work in that paradigm, right? It has to be.
Yeah, so you typically need some sort of parallel database or a parallel framework like Hadoop, for example, to be able to handle it. And as you've got here, right, one of the reasons why it's so big is just because sort of it's structured and unstructured data gathered from sort of big onslaught of data from sort of the internet, broadly speaking, as well as sort of sensors and non-human agents on the Internet of Things. Okay, so what do we, that's what big data is. It's stuff that we can't fit into a laptop in a sense. What do we do with it? Where do we put it? How do we use it?
Sure. Well, do you want to maybe talk about why big data is a thing? Stephen, I know you've been in the database world for a while. Like, from your point of view, can you talk through?
Yeah, I think just as you were sort of hinting earlier, right, this sort of, the advent of e-commerce, starting, roughly 20 years ago, and the Internet of Things sort of coming a little bit after that, has just generated a ton of data, both structured and unstructured. We've also got the mechanisms, the technologies for dealing with that. These sort of parallel computing frameworks, which are a lot cheaper these days through the advances of companies like Google and Yahoo in the early days with Hadoop. And then we've got these machine learning techniques that have become more mature, including the ability to actually have those run in parallel. And then I think it's in the water, it's in the air, right? So people have heard of the Netflix challenge. Everybody experiences the Facebook algorithm. There's famous stories about Target predicting people being pregnant. So I think it's just out there.
Right. Well, then I think the next question is what you just said too, which is, what do we do with big data, and where is big data? And I think it'd be important to sort of go over some of the key players in the space of big data, right? I know Amazon EMR is a big data database to house these things, right? Amazon, Google, Microsoft, these are sort of big name databases and companies.
The way I like to think about this is that, very crudely speaking, right, there's sort of the structured world of databases and the structured and semi-structured world Hadoop and NoSQL and so on. And so you've got Hadoop, and coming along with that, Spark out of Berkeley as sort of like a more flexible and rapid, faster framework for doing compute on parallel frameworks. So you got Hadoop and Spark, and then you've got the cloud-based flavors of that, like Amazon's EMR and Google's Dataproc and so on. Then you've got the traditional databases, and of course, cloud versions of those like Redshift and Azure SQL Data Warehouse. And then you've got sort of the NoSQL forms like Mongo and Cassandra. So that's sort of how I would sort of categorize it.
Mm. Okay, and then I think the next question is, okay, so this is sort of where you store the data. What do you actually do with it, and how do you actually process that data? So these are some examples of companies or frameworks, software that help you do that. You'll notice I have Spark on here twice. It was not an accident, maybe, but I think it is fitting because Apache Spark is really one of the oldest, or at least most prominent players in the game in terms of a big data processing framework, right? So you have your data that's spread out and partitioned out, right? Spark and MapReduce, Flink, Hive, right? All of these sort of let you interact with that data in a familiar way, but that data is spread out, but you're still able to do computations on it, but those computations are also spread out too, right? So you have this notion of parallel processing.
Maybe a quick way of summarizing this would be to say that in the early days, we had sort of MapReduce as a way of dealing with big data, and it's a pretty unfriendly way of being able to deal with it. And since then, you know, there's been convergence in some ways back towards SQL as sort of like the mainstay of perhaps one of the most popular languages of data scientists, and Spark as a richer, easier to use, more flexible framework than MapReduce. So there's plenty of languages, including just plain old friendly SQL for dealing with big data. So good, yeah, that's a whistle-stop tour of big data, but hopefully that's useful. And it's certainly something that I think has matured a lot and is now sort of pretty much omnipresent at sort of Fortune 1000 companies. And most data scientists, even coming out of school, have had some experience of Spark, PySpark, and things like, and SQL interfaces like Hive. All right, Nico, let's get started with our main session, which you're going to be presenting on neural networks. It's another area that I think people feel like they need to know a lot about, but it's pretty confusing. And I thought today would be useful just to give us a high-level overview of the world of neural networks and where do you get started and where do you get next. So tell us about it. You've been doing some work in this lately.
Yeah, so like Steven said, I'm going to be talking about neural networks, but specifically, I think I'm going to talk about something that a lot of aspiring data scientists or folks who dabbled in machine learning have experienced before. And I know when I first started this, I went through some sort of variation of what I'm going to go through. And it starts out with Googling, right? What is machine learning? Explain like I'm 5, what are neural networks? And then you move into, will AI take over the world? And then once you sort of figure this out, you learn about sort of the hello world of neural networks, which is known as the MNIST data set, a data set of handwritten digits where the goal is to try to create a neural network to classify what digit is being written. But of course, you know, when I found out about this, it opened up a whole nother rabbit hole for me, right? What is TensorFlow? You know, when I try to install TensorFlow, it isn't working on Windows. Somebody help me.
Okay, so Nico, remind us of where we got started with all of this, right? Just a quick 30-second overview of basic neural networks.
Right. Well, neural networks are a type of machine learning, right? And so you can see in the background here, it's a way of processing sort of unstructured data and feeding it through a network, right? The common way of describing neural network is it's akin to the human brain of neurons, right? You have different neurons all sort of scattered throughout, and they're all connected to each other. And as you feed information in, they all sort of blink up and connect, and you have these links in between each neural network, in between each neuron, and you have these different layers, right? So the first hello world, or first introduction to this is an MNIST data set. So if I'll go to my next slide.
I mean, it doesn't have to be, right? I mean, this applies to any data set, but I think MNIST is sort of the classic one that people get started on, as you say, the sort of the hello world.
Right. Yeah, exactly. It's a natural starting place for a lot of people. If you look up how to get started with neural networks, MNIST data set of these handwritten digits is a great example or great starting point for neural networks. But today we're going to be taking it sort of a step further, right? This is assuming that you've gone through this first step of neural networks. I mean, I know when I went through this, I followed some online tutorials and was able to train a neural network to classify these images of handwritten digits. But then I thought, you know, what's next, right? How can I take this to the next step? How can I take it to the next level?
Yeah, my understanding, right, is that the type of networks that you typically use for these sort of hello world examples, these sort of multi-layer perceptrons, are kind of almost rarely used these days. They're almost too basic, but it's useful to understand them. The way I think about them, right, is they're almost like lots of little linear regressions sort of networked together, each one receiving the outputs of the previous layer, the first layer just being this sort of string of digits that represents the image. And then they sort of just transform that, much like a regression does with a bunch of coefficients. There's some sort of activation function that makes it a little bit more complicated to decide what actually goes on to the next layer. But you're just sort of feeding these forward and eventually coming out with sort of a number or a classification at the other end. And then you just sort of like constantly run through it, sort of penalizing for some sort of error, and then adjusting those coefficients, reweighting them, and eventually coming up with a model that's better. So that's sort of the basic example. And I think for image recognition, how do people move on from those sort of basic networks?
Yeah, I think you're exactly right, Stephen. Those sort of multi-layer perceptual networks are good, but they sort of fall flat when you're faced with more complex.
Yeah. So let's move on to the next one, then, Nico.
Sure. So how you would move on? Sort of the next step is what's known as a convolutional neural network. And it's just a variation on a multi-layer perceptron network, right? And the key thing about this network is it's really good at picking out or identifying patterns in data. So it makes sense, right, that it's good for image analysis because, right, they're pretty spatial in nature. So CNNs are a lot like regular neural networks, or sort of the basic ones. They're still made up of those weights and biases, and just like Steve had explained, you still have those mini regressions, right? And you back propagate. That's all still there. But the difference about CNNs is in the name, right? Convolution. There are two main parts that make up a CNN. And the first characteristic is that some layers in there, if I go back one slide, some layers are convolutional layers. And then in addition to these convolutional layers, you have things called filters. So these layers perform some sort of transformation on the input data, and then that transformation is based upon the filter that you choose. So there's a lot of new words there, and there's a lot to unpack. Like, what is a filter, right? What actually is a convolutional transformation? But I think the first thing that we have to answer before that is what actually is a pattern. Right, I mentioned that CNNs are good at pattern detection, but what does that mean, right? Well, images have a lot going on. They have circles, like if you look at that eye, or round edges like the ear. These are really complex things. And an example of a pattern might be these, or it can be just an edge, right? So here we see an example of edge detection of the input image. So an edge might be an example of a super simple pattern that a CNN might identify.
So you're sort of breaking down complex images into smaller and smaller parts to the point where they become pretty easy to recognize, like an edge or a circle, something like that.
Yeah, exactly. And one thing you'll see in a CNN is the way that you do that, Stephen, is you have different filters that identify different patterns, right? And so in the context of a CNN, the complexity of your filter will sort of increase the more layers you have. So you might do edge detection in your first layer, on your first convolutional layer, and then in your second, you might actually do a more complex shape, like a circle or maybe a polygon or something. And then these layers sort of stack on top of each other, right? So edge detection plus a circle or polygon might equal something else. And then your third layer is now a filter that identifies that combination. And so now the question is, okay, we sort of understand how to, or what's going on in terms of identifying these different features, but now what's next? And what's next is the actual convolution, right? So the purpose of convolution, where that name comes from, is sort of windowing over the input image. So if we go back to this slide and we think back to our MNIST data set where we have a picture of a number and we treat each pixel value as an actual value, then our filter, our little 3x3 matrix, windows over that input image. And so it has a way of sort of sliding over and looking at each portion of an image. And you can sort of see that in action here, right? So it essentially maps over the image. And depending on your filter, it highlights whatever feature it's looking for, whether it be edges or circles or more complex shapes. So this is sort of the heart of a convolutional neural network. And you can take many of these filters, right, for edges or circles or combination, but then all of a sudden you've sort of multiplied your initial image, right? Instead of having one image, you now have 2, 3, 5 new images that highlight different features. So the next step is feature reduction. And we see that through the pooling layer. So you have your input, your convolutional layers, and your filters. And then after all that, you have a pooling layer, which essentially just reduces the amount of data, right? You've generated all these different images, but that's too much. There's too much noise there. So the pooling layer lets you sort of sample down, reduce the dimensions, and get a smaller data set. There's a couple different ways to do this: max pooling, average pooling, sum pooling, and they all just
to keep it simple, and then let's move on to the next one, so we make sure we have enough time. But just maybe the sort of dumb version, as I hear what you're saying, it's like you have all these activation functions, these little sums of weights in a standard neural network, and now you're introducing this idea of slightly cleverer functions, right? That kind of know what they're doing, and they perform specific functions to identify these features. And you're just making the neural network a little bit more specialized. That's sort of the basic idea here, right?
Yeah, I think that's right. And just to close on that, right, if we look at a high level view, right, you have your initial input image over here. You have these convolutional layers where it expands the image with all these filters, and then you shrink it back down for pooling. You expand it again, and then you shrink it back down for pooling. And then all of a sudden, you're back into this world of familiarity, right? You're back into just a regular feed-forward network with those weights and back propagation and all of that.
Nice.
So that was a whirlwind overview of CNNs, right? Again, it's a huge world, and there's so much depth to it. So I think for the sake of time, we'll move on to a new one. And so CNNs are used for image analysis, right? Because they're very spatial. But there's a lot more problems out there, right? One of the big problems is video analysis, right? Or looking at issues or problems that have a temporal aspect, something that happens over time. If we trained a CNN to look at this image and the object was to figure out which direction is this circle moving, a CNN would be lost, right? It would be able to identify that this is a circle, but each image that's fed to a CNN is independent from one another. And so when faced with the task of figuring out which way this is moving, this is all it would see. So income, a new type of neural network, a recurrent neural network. And the recurrent neural network, instead of taking the input as individual sort of agnostic images, a recurrent neural network has a memory, so to speak. The idea is really just to be able to make use of sequential information like this ball moving. So an example of this might be text analysis, right? So if you have a recurrent neural network and the input is some line of text, it might be, what time is it? And the way that a recurrent neural network would work, or sort of analyze this, is sequentially, right? So you break up the sentence into individual words, and you'd feed what to the neural network. And then the network would sort of take this as input, and it would produce an output, right? And then the next word is time. So if we go to the next step, we would take in time, encode it, sort of push it through the network, and then have it be output. But you notice it has part of the previous input as its input. So it sort of a chaining along. So if we go through the rest of the sentence, we can see it sort of build up over time, and each concurrent word has influence or has output from the prior word, right? So the whole point of a recurrent neural network is to be able to handle time, right? To be able to understand context. And it does this by taking in input and sort of feeding it back through itself and having importance put on things that came before it. So that's recurrent neural networks in a nutshell, but there's a bunch of different types, actually. If you think about the different types of temporal problems, right? Obviously, a simple one is one-to-one, which is just like a regular sort of machine learning problem. Where it starts to get interesting is a one-to-many relationship. So this is a situation where there's multiple outputs for a single input. Meaning, in the world of recurrent neural networks, this might be music generation, right? So the input to the network might be a single musical note, but the output is a whole song, right, or a whole chorus. Another example would be many-to-one. So this is sentiment analysis, essentially, right, where you have an input of words, and your output of the recurrent neural network is, good or bad. Right? Is this a good sentiment or bad sentiment? Where it really starts to get interesting, though, is a many-to-many relationship. So there's two cases here, right? The first is where you have input and output layers of the same size, but really an interesting one here, and one that has developed quite a lot, is the case where they're uneven, right? So where your inputs don't equal your outputs. An example of this is machine translation, right? If you take in English the words "I love you" and you translate that to Spanish, it's "te amo," right? So you have three words as input, and running it through a recurrent neural network, your output is then two words. And these are just sort of different scenarios or realms of machine learning that require recurrent neural networks, and that require different structures or different architectures of networks.
But the common theme, right, is that they're sort of sequential in nature, some element of I guess, a time series in some ways. I mean, maybe does it apply also to videos? So like maybe, is it
Totally.
Okay, right.
No, totally. I mean, anything that has a time dimension, right? Something where time and context is important. So if you think, I mean, one of the projects I worked on was analyzing football plays, right? So over the course of a football play, there's things that happen, right? There's a start and there's an end, and there's things to be expected at the start when everyone's still. And there's things to be expected at the end when everyone is tackled and on the ground, right? So that's an example where it's video data, and time is definitely an important factor.
Okay, and again, I hate to hurry you along, but that's the second example. What other examples from this phantasmagoria of neural networks?
Well, the third example is called an autoencoder. So autoencoders, compared to recurrent neural networks and convolutional neural networks, are actually pretty simple. So this is a relief. They're basically a form of compression, right? Autoencoders allow you to take an input data set, compress it down into a smaller format, and then that smaller format is essentially the core components of that data set. And you take those components and you basically re-project out the input data set. So it's a little bit of a weird concept, right? All of machine learning and neural networks up to this point are kind of like, you have an input and then you have a predicted output, right? autoencoders are different because you have an input, but your predicted output is trying to be your input. You're trying to recreate your input. But the way you do that, again, is by compressing down to sort of the core components and then projecting it back out.
Nice.
And this allows us to do a couple things, right? There's a few use cases here. One of the main ones is anomaly detection.
Yeah, we're actually going to cover this in the next Dr. Data Science session, so this is a good preview.
Oh, well, there you go. Yeah, autoencoders are perfect for this because what it allows you to do is if you have a good model, right, and if you've actually been able to compress your data set down and project it back out, you should have a perfect data set at the end, right? You should have an expected data set. And so to find anomalies, you take that produced data set and you compare it to your initial sort of input data set and you find the differences, right? And any entries or rows where there's a big difference as to what was input and what was expected, you have something called a high reconstruction error. And any entries with a high reconstruction error are most likely anomalies. So I'll just sort of quickly go through the components, right? You have your input, you have an encoder, which takes your input and compresses it down into the center sort of bottleneck. And then you have a decoder, which projects it back out. And then you have your reconstruction error at the end. Another example here, another use case is image denoising. So if you have an image like this, but there's sort of dirty pixels all around and it's hazy, an autoencoder will, again, sort of get its core components and then project it back out. And it'll get rid of the noise or sort of the non-core components of that image. It's actually pretty similar to PCA, if any of you are familiar. There's a lot of different types of autoencoders, just like neural networks, or just like recurrent neural networks. There's just a lot of variation depending on what you're trying to do. You can see the denoising autoencoder, variational autoencoders. Again, it's a very deep field. And I think that is sort of embodied throughout neural networks, right? It's not just autoencoders, it's everything. These are examples of different neural networks that are used for very specialized problems, right? CNNs and autoencoders and RNNs are used for broad applications of issues. RNNs, temporal, CNNs, sort of image analysis. But you can get even deeper and more niche than that, depending on what problem or issue you're trying to solve.
Right.
So yeah, that was covered a lot.
My takeaway from this is that, you kind of have to know what you're doing, at least at a high level, before you get into neural networks, by which I mean, be aware that they're pretty complex and highly specialized at this point. And so knowing that there is a choice to be made is kind of an important part of applying these things. And also knowing that, make sure that neural networks really are appropriate and that some simpler model that's perhaps a little less complex doesn't fit the bill.
Mm. Yeah, I think that's definitely right.
This has been a very rapid, but I think still useful sort of like initial introduction. So at least we've sort of helped to orient ourselves through the world of neural networks. Nilima, do we have any questions? Looks like we got at least one or two, yeah?
Yeah. So we have a couple of questions. First one, how sensitive are neural networks with respect to input data quality?
Ooh, that's a good question. Do you want us to take a step? I got actually a real world example of that, Nico, but do you want to take a first step?
Sure. I mean, I think it depends on, everything's on a spectrum, right? So I think it depends on how bad your data is. I mean, if you have a terrible quality data, I mean, I don't think any model will really dig you out of that hole, right? There needs to be some level of data cleaning and feature engineering. But with that said, I mean, there are different types of neural networks that are more resilient to dirty data. I don't think there's sort of a catch-all sort of answer for this. But I don't know, Stephen, what do you think?
Well, I'm not an authority on this, but I do have one example from our work with Perkin Elmer. It's a partner of TIBCO, and they've been using TIBCO data science along with neural networks for doing image processing and image classification for medical images used in sort of clinical trials. So they'll have images of cells, for example, that have been exposed to different treatments and also are representative of different biological statuses, basically disease progression, for example. And they want to classify those images. And the process they had beforehand was to manually cleanse the images and then to break down those images into individual cells and then the cells into individual features like the neurons or the membranes and so on. And then to sort of turn those into numerical metrics and then feed those into a standard model. Well, neural networks kind of does that all for you. It's very good at determining the sort of messiness in the, or filtering out messiness in the input images, at extracting the features out, at turning those into numerical metrics and features that can be then put into the remainder of the neural network. So I think it's a good example of how the input data there is pretty messy, because you often have images that are out of focus or that have other sort of artifacts in them. And the neural network just kind of takes care of it for you.
Yeah, I just want to add on to that one last thing, which is, I mean, I watched a movie. It was a Steven Spielberg documentary about World War I, where they took really old, grainy film, and they passed it through this giant autoencoder, and out came this super clean, just totally restored version of this old film. So I guess that, yeah, it's another example of, you know, quite literally dirty data, and being able to clean it and handle it and have a good output.
It kind of sounds like magic. Well, Nalima, I think we're done. We went a little bit over, but I think that was useful to address that question.
Yep, this makes sense as we are talking about neural networks. Stephen, let's give a preview of what our next topic for the next month session is.
Yeah, Nico mentioned using autoencoders for anomaly detection, and we're actually going to focus on anomaly detection in our next session in December. And so that'll be a general survey, as we often do, of that subject, and we're going to look at different approaches, not just neural networks, for being able to identify anomalies from data. So essentially, it's sort of a collection of supervised and especially unsupervised methods for rooting those out of your data. So that's next month.
That's interesting continuation topic. One last question here. So do we have any sample types of codes on neural networks that we could hand over if anyone is interested in the audience?
Yeah, I think we do have some examples, actually, including the autoencoders that are on the TIBCO exchange. We have some accelerators there that you can plug into Spotfire. Nico, are you aware of any others?
No, not that I'm aware of, Stephen. I think those are really great places to start, though.
Yeah, and also we do have some examples of using neural networks in TIBCO data science platforms, some sample workflows. We don't have those published, I don't believe, but you're welcome to contact me to get those, and I can distribute them.
Thank you. Thank you for attending the session. Thank you, Stephen and Nico, for the wonderful presentation. Have a nice day and rest of the week, everyone. Thank you.
Thanks, bye.
Thank you.